So I've already gotten the answer to this one started a little bit in the last example here, where I claimed that if you have n molecules in a box and they're all moving at random, that the pressure on the side walls of that box, and it turns out that could be any of the walls really at this point, because we're not just having a molecule that's bouncing back and forth horizontally, so it's also the top walls and the other, I guess, the walls that's facing us and the one behind that one, all those would have the same expression at this point, but would be equal to the number of molecules times the mass of the molecules times the average of the velocity squared over 3 divided by volume. Maybe that can be simplified. I haven't bothered to do that yet. Maybe I can do a little bit with this, because I want to say this notation is going to come up a little bit later, not yet in this example, but I want to clarify something. Let's see, if I look at this, this is, I think I'm just going to pull out that 3 and say, okay, there's like a 1/3 n, and then there's m, and this v bar squared, another way of looking at this is actually equal to VRMS. So we might remember that on the key concepts slide, there was this thing called VRMS, which was root mean squared, but it's actually equal to VRMS squared, because it turns out if you say, okay, take the square root of the average of these squares, that's literally what root mean squared means. But in this case, if I take the square of that, it's like I'm undoing that square root that I just said. So the square root of the root mean squared, the square of the root mean squared is really just the mean squared in a sense, which is what this thing is. Oh, and oops, I've been talking for a while here, and somebody might be thinking, wait, don't you need a volume in there somewhere? Yes, I still need to have that volume, so let me make sure to add that. But we're going to do an example a little bit later where we're going to be asked to find VRMS based on the formula that was on the key concepts page. So this is where you can see already that connection being made, but this is not that formula. This is still a lot of, I know there's a lot of garbage here perhaps, but let's look at the answer here, since this is a formal example. And what we see here, although maybe not written exactly the way I have it over here on the whiteboard, but this is an expression that is equivalent to what I've been writing, still using the bar notation rather than switching to RMS, which we'll do later. But it says, okay, that's what pressure is equal to, and therefore, well, what did I do here? I did something maybe a little bit mysterious that in some senses, if you don't know where you're going with it, you would say, why would you do that? And basically what I did is I multiplied by 2 in one place and divided by 2 in another place. But why might that actually make sense is this expression looks an awful lot like kinetic energy, except that there's a bar over the v squared. And it turns out that's my goal, because if this is really, if bar of v squared is like the average of the velocity squareds, and if we're talking about a collection of molecules that all have the same mass, then it turns out this expression is actually the average kinetic energy. Then I just multiplied both sides by volume, and I got PV is equal to this. And that's kind of cool, because pressure times volume also is in the ideal gas law. So if I compare PV is equal to this stuff here to the microscopic form of the ideal gas law, PV is equal to NKT, then I can take the right sides of those and set them equal to each other. And that's what I've done here in the last line, is I've said NKT is equal to this 2/3 times N times this 1/2 mv squared, which if we interpret that 1/2 mv squared as the average kinetic energy, let me write maybe a couple things here, because like really what I've gotten to there in that last line is I've gotten to NKT is equal to 2/3 N times the average kinetic energy. So I can cancel off those n's, and then if I multiply both sides by 3/2, I would get that the average kinetic energy is equal to 3/2 kT. And this really is maybe the first big result coming from the kinetic theory of gases. And the other formulas and results that we're looking at that were on the key concepts page, many of them can be related back to this one as sort of the first step to getting to them.